Welcome friends to TechTide Digital Lifestyle. Today's special video is a complete revision lecture where we will go through all the important formulas and equations used throughout our induction motor playlist. This video is especially helpful for ETO and COC examination preparation, marine engineers technical interviews, and quick revision before tests. In this lecture, we will only focus on formulas, symbols, and how to remember them easily. Keep your notebook ready and follow each slide carefully before starting this lecture. Please subscribe my YouTube channel. Let us start with the most basic formulas related to speed. Synchronous speed is represented by ns and is calculated as 120 times supply frequency divided by number of poles, and its unit is revolutions. Rotor speed is represented by nr and is always slightly less than synchronous speed, and it depends on slip. Slip is written as s and is defined as the difference between synchronous speed and rotor speed divided by synchronous speed. Slip has no unit and is usually expressed in per unit or percentage form. These three equations are extremely important because almost every numerical problem in induction motors begins with speed and slip. Now we move to rotor quantities. When the rotor is running, the induced electromotive force in rotor conductors is proportional to slip, so rotor EMF at slip s is equal to slip multiplied by the standstill rotor EMF. Similarly, rotor reactance at slip s is equal to slip times the standstill reactance. Rotor current is calculated using the impedance of the rotor circuit, which includes rotor resistance divided by slip and rotor reactance. Here, E2 is rotor-induced voltage in volts, R2 and X2 are rotor resistance and reactance in ohms, I2 is rotor current in amperes. Next is the most important equation of induction motor operation, the electromagnetic torque equation. Torque is represented by T and is measured in Newton meters. It depends on rotor-induced voltage, rotor resistance, slip, and synchronous angular speed, which is represented by omega s and measured in radians. The equation clearly shows how torque changes with slip and rotor parameters. This formula helps us understand starting torque, running torque, and also explains why torque first increases with slip and then decreases after a certain value. Now we look at the condition for maximum torque. Maximum torque occurs when rotor resistance divided by slip becomes equal to rotor reactance. From this condition, we get the slip at maximum torque, which is written as Sm and is equal to rotor resistance divided by rotor reactance. The value of maximum torque is proportional to the square of rotor-induced voltage and inversely proportional to rotor reactance. A very important point for exams is that maximum torque does not depend on rotor resistance directly, only the slip at which it occurs changes. Now let us see the power flow inside the induction motor. Air gap power, represented by Pg and measured in watts, is the power transferred from stator to rotor across the air gap. A part of this air gap power is lost as rotor copper loss, which is represented by PRCL and also measured in watts. The remaining part is converted into mechanical power, represented by PM, and is equal to air gap power multiplied by 1 minus slip. These three relations are extremely important for calculating. Input electrical power of a three-phase induction motor is calculated using the square root of 3 formula multiplied by line voltage, line current, and power factor. Input power is measured in watts. Efficiency is represented by ether and is the ratio of output mechanical power to input electrical power. Output power is equal to mechanical power developed minus mechanical losses like friction and windage. These formulas are commonly used in efficiency calculations. Now let us revise the equivalent circuit parameters. Stator impedance is written as Z1 and consists of stator resistance plus J times stator reactance. Rotor impedance referred to stator is written as Z2 and includes rotor resistance divided by slip plus J times rotor reactance. The total impedance seen by the supply is the sum of stator and rotor impedances and is written as Z equivalent. All resistances and reactances are measured in ohms, and J represents the imaginary operator. From no load and blocked rotor tests, we calculate many performance parameters. At no load, the input power is approximately equal to core losses plus mechanical losses. During blocked rotor test, the input power is mainly equal to copper losses because the rotor is not allowed to rotate. Full load slip is calculated using synchronous speed and full load speed. These formulas are extremely important for laboratory experiments in ETO or COC numerical. Now let us revise starting and speed control formulas. Starting current is directly proportional to supply voltage, while starting torque is proportional to the square of supply voltage. Synchronous speed again depends on frequency, so by changing frequency we can control motor speed. In variable frequency drives, the ratio of voltage to frequency is kept constant so that air gap flux remains nearly constant and torque. This brings us to the end of our complete induction motor formula revision lecture. Make sure you practice these equations regularly and solve numerical problems based on them so that you feel confident in examinations and practical work. If this video helped you, please like the video, subscribe to TechTide Digital Lifestyle, and comment which topic you would like us to cover next. Thank you for watching and happy learning. Please like and comment this video and subscribe my YouTube channel TechTide Digital Lifestyle.